Thanks, Michael. Okay, I'm just going to present one project which is very recently, at this stage you see in the picture, called the FabPod. And I come from the Spatial Information Architecture Laboratory, which, as Michael said, is led by Mark and Jane Burry in Melbourne, and certainly centred around their work on the Temple Sagrada Familia. And the research lineage for this project also goes back to Antoni Gaudí. There's written evidence that the hyperbolic geometries in this project, Gaudí was convinced that these had particular diffusive properties, and it since happened that when the interior was opened in late 2010, musicians anecdotally said, "Hey, this interior is very highly diffuse and a great space musically." So this lineage led to a smart geometry workshop in 2011 called Responsive Acoustic Surfaces. 4 days, and digital workflows were developed, and from 1 to 10 printed prototypes. You see at the top looking at tessellation patterns for hyperboloids. These 1 to 10 panels can be used for acoustic testing because sound is scalable. And they also built a one-to-one demonstration piece, built a series of these components with hyperboloid faces. So I wasn't directly involved in this, but the person who did lead it was Brady Peters, whose work's been focused on acoustic diffusion particularly. So I'll just quickly show you two animations from Brady that kind of describe acoustic diffusion and its potential. So on the left you see an interior space with a sound source in the middle, and you see the wave behaviour of sound, and you see particular hotspots forming, etc. And on the right, you see that same similar space, but with an articulated wall, and you get this temporal effect on the sound, in which you get a diffusion and scattering from these surfaces in which hotspots don't occur. And his contention in his PhD work is that this is actually a very desirable space. So this takes us to the next iteration of this research, which is the FabPod. So this is the image you've got in the program. So we had the opportunity to extend this research to build a prototype for a meeting space. And this was a great opportunity to take the existing research out of some sort of demonstration pieces and attempt some real-world applications. So an acoustics was central to the brief. This sits inside an open plan office environment, an open knowledge environment, as they're sort of called these days in the jargon. And the brief was asking for a particular, it was centred on acoustics. So looking at good speech intelligibility internally, and providing a space where there was privacy. So this is an image, but I'm here to describe a system with which we move towards that. And the prototype sort of addresses two dichotomies. One between architectural practice and academic research, which Bob and Rory Glidden highlight in their Fabricate publication. That there is quite a tension here, and this is to be a permanent installation, so this isn't just a pavilion. But also, this is to some degree between a product and an architectural project. This isn't just a one-off, this is a system with a view that there will be further iterations and further pods required, as this is a pretty generic problem. So the task at hand is to develop this workflow system, and we're attempting to make it as open as possible. So it's open to external requirements, and it's highly modular in the way it's set out. This is a sort of broad overview. And there are two key types of feedback. One from acoustic simulation in the design process, and the other from fabrication and making processes into the design process. So but the bigger picture for the project and the bigger picture for this design system is actually beyond that system, to engage post-occupancy testing, to engage physical testing of the as-built piece acoustically, but also socially, and to go back and address the parts of the system, but also to go back and address the brief itself. Because the performance goals for this sort of thing in an architectural context are not all that clear. There are certain privacy requirements that are clear, but in terms of defining what a good space acoustically is, it's still very, very difficult to identify. So So I think the project really, the system came back and started with taking the component logic from the original research forward. So we wanted to develop a series of cells, each with a hyperboloid face on one side, a planar face on the back, and a timber frame holding these together. And a serious limitation of early research had been understanding these, the geometry. So we set up a geometric space in which we could design. These are hyperboloids of one sheet. They're circular hyperboloids as opposed to elliptical, so they're rotated around a single axis. And we were looking for instances where these hyperboloids might intersect with each other in planar curves. So the one on the far left, where they're sitting next to each other on a planar surface, is the case. And on the far right, where they're sitting arranged on a sphere, also gives this result. And the planar intersection curves is precisely related back to this image of the fabrication technique, that we felt that in the means we had, we could develop cells with sheet sides, but we couldn't start to deal with curved geometries in that aspect. So this became a couple of limitations. So we looked at arranging hyperboloids all focused into one sphere, so we could get a series of planar curves. And then where one sphere left to the other, we just needed to make sure that there was a clear mirroring situation where we also had a planar curve. So this gave us a design space, a geometric space of two types of families for these pods, depending on sort of which side of the sphere we were using. So this set up a geometric space in which we could design, and we set up a series of design tools. These were parametric models, grasshopper models that are sort of in the box in the middle of this diagram. And these three tools allowed a designer to go through and design the overall form, distribute material and surface articulation onto a designed pod. And the interesting thing about this breakdown of models was that it interacted with a particular workflow into the acoustic simulation. So acoustic simulation works quite well on broad overall forms, but it can't handle this sort of articulation very well. So the first tool could plug into a plugin called Pachyderm, which has been developed by Arthur Van Harten at Norman Foster's office. Beyond that, with the surface patterning, we had a workflow with Brady through to MATLAB to identify scattering coefficients. And finally, once we got to some more detailed geometry and materiality, we could take it to a commercial acoustics package, this time Odeon, and get some feedback to verify our other simulations, as well as to sort of push what Odeon could do. So in parallel to that, we did do some laboratory testing. This is in RMIT's labs, and this is basically the one performance criteria we could control, and that was transmission loss. So we had to make sure that our physical cells were stopping enough sound getting through, otherwise the effects of the surfaces would be completely irrelevant. So here are some of the images of the digital tools on the left, generating form, and on the right, looking at the surface articulation. And you'll see that we had a whole lot of constraints from the fabrication, sort of maximum distances, like sizes we could make and angles we could handle, sort of being highlighted in pink. These are some basic, from the first tool, some basic simulations in Pachyderm, and looking at some quite generic acoustic criteria of reverberation time and early sound decay. And at the same time, Brady was working through this articulation and testing out scattering coefficients of different materials through his little workflow to MATLAB. And this was the rough mesh type that we were able to generate from our model and put into Odeon. So these acoustic, as I said, these acoustic simulation packages are really designed to handle flat surfaces, and something that's doubly curved, they really don't handle very well at all. So this was about as crude a mesh as we could handle as we could use within the time frame that we had. So this is a simulation in Odeon. And we took this to a workshop, an intensive workshop for a week. We took these tools and we sat down with 20 students. This was our sort of generative system, if you like. It's a very complex decision space, so we didn't have all that many tools that were automatically sort of generating options. Instead, we put our computational power into making things real time, so that for example, we had a spherical Voronoi algorithm that allowed us to tessellate this thing and change tessellation across a surface and for it to update in real time from a sort of flat surface to the 3D through the grasshopper model. But this week wasn't really about a process of optimization as such, but a process of a deepening understanding of the acoustic performance and what this space might sound like through the engagement of this tool. So in that, if anything, it was a deepening understanding of the problems we were facing. And in that way, involves some developments of rules of thumb, identification of key criteria we should address, and design strategies that we might adopt for these. So at the end of the week, this was a selected iteration that we picked and said, right, this is what we're going to build at full scale. This is a plan. It sits inside an open plan office space. This is a small section of it. It's 60 metres long by 10 metres wide. This is the architectural sort of space through section. And we, in parallel to the design tools, we'd be developing the fabrication workflow. So we were able to take actually a text file abstracting the information of all the cells in the grasshopper model and take it to a CATIA model. In this case, we're trying to be quite software agnostic, and certainly this level of detail was highly important to the fabrication process. Yeah, but you can see that we still had some issues. You see the brown backs where the little scoops for fixing have not come out. So we're still, certainly wasn't a straightforward process. But this, if anything, this is where industries such as aerospace can inform architecture in terms of the processes that we can engage in design. But the fabrication of this kind of thing actually has much more to do with furniture making and product design than it does aerospace. So we had access to a 5-axis router at RMIT and another one industrially. This meant we could sort of flank cut at any angles we wanted, both with a tip and with a flank. So we could basically take the furniture technology of miter jointing and be geometrically free. So sheets were coming off the machine with the various parts, and these timber cells were being assembled. And I think this is where I should probably flag the other sort of co-collaborator on this project, John Cherry, who, while I'm the sort of young architect who's got some digital skills in some way, John's been making things for 40 years, making furniture and architecture, and he really pushed us that every miter joint had to come together tight. He pushed us to work to a tolerance of 0.1 of a millimetre. That's what he thinks he can see, and that's what the machine can cut to. So for us, understanding this assembly process and developing this was very important, and jigs were fundamental to this. So that was the timber frame assembly, and with the right jigs we actually got students assembling these, making sort of 15 to 20 in a day, no problem. The Hyperboloid faces, we went and looked at some industries and processes that supply product design. This rotational, this sort of rotational symmetries we're dealing with, metal spinning was a fundamental one. So this is on a lathe, a flat sheet of metal stretched back over this MDF tool. So we provided metal spinning shop with basically just a laser cut guide for them to machine down a tool to that shape. And then these were the Hyperboloid faces that came off that and were subsequently anodized. The other thing we were interested in was plastic forming. This seemed to be very relevant to this scale. In this regard, it was cheaper and easier for us to actually make the mould, although it did take us 4 attempts to get it right, between students putting screws in the wrong place and machines not being properly calibrated. So this is a plywood mould. Plywood's very dimensionally stable. And this was machined in-house at RMIT. So we pushed it sort of sizes as much as we could, sort of 300mm depth and a 1200mm width. That's also, 1200mm is also what these plastic sheets come in. So there are 2 types of plastic. One is, on the right, a white acrylic, which is formed. These are formed through a vacuum process, but also RAM assisted by an arm centrally. We're dealing with convex geometries. On the left is a product called Echo Panel, with which we worked with the producer of this. It's 100% PET, but it's felted in its texture, and it's actually designed as an acoustic absorber. So they sort of said, we know in theory you can form this stuff, we just actually don't know how to do it. So John set about doing some tests and talking to some manufacturers and worked out how to do this. So very quickly the workshop at RMIT became a mini factory, employing students on a very regular basis. And as I said, we had 180 of these hybrid components to make these frames and faces. So the timber frames actually we assumed were going to be the logistical nightmare, but students were putting these together at 15 to 20 a day. So between 6 of them we were done in a couple of days. What did become difficult was the actual finishing of the Hyperboloid faces. So here you see sort of arrays of these things. So we've got 180 related but geometrically unique pieces in the faces, and in the end we were able to rough cut all the Hyperboloid faces, and then each component simply put through a table planer to make sure that everything was coplanar with the frame. So this is some of the geometric flexibility we were able to deal with the white acrylic. Okay, and the Echo Panel, some lighting details added. These oculi, 60 of the oculi. So these were quickly moved to site. So all 180 assembled, and then we went away for Christmas. Came back and laid out sort of the ground level. And this point in the assembly actually takes a lot of time to make sure that you've got your set out right. And once we had this set out right, we could start to move forward quite quickly. So the first connections, each cell is bolted with a single bolt face to face. So connecting the bottom rows was quite straightforward, but getting the accuracy right was very difficult. And you can see that between each of the cells we've allowed a 3mm shadow line. We've added a little spacer piece. And this helped us to deal with the tolerances that we knew we were going to get with a student project. And I'm happy to say that we're within sort of 0.5 millimetre of that 3mm everywhere. So this is the scene after the first day, and there was 7 of us assembling. And this is after just over 2 days. So this is, this is 2 days to put all the components together. Another 2 days to actually wire the whole thing up and get the electrician in. So this is the interior of the space. It's only been as such for about 3 weeks, and we still have a few final touches to add. But the final production is very accurate, as I've been saying. We're all very happy with that. This is it sitting within the larger office space. If anything, the biggest challenge has been these external panels, which are all Velcro fitted. So actually getting the tolerance on Velcro is about 0.1, 0.2 of a millimetre itself. So getting these to fit tightly has been difficult. This is the big research team that's involved, and some of these are companies, so there's multiple people involved. But this basically takes us back to we're now at this sort of larger stage in the design system, where we're at the right hand end. We're looking at the post-occupancy testing and looking to feed this back into the system. So the testing has started. We've already done a 3D scan, as Bob's been talking about, and we are about to start in situ acoustic tests, but we're very interested in sort of acoustics as a communication model. So we have a new professor of digital ethnography at RMIT, and she will be engaged in starting to evaluate this sort of space and its usefulness, the design value, as a space. Thank you.
Thank you very much.